I start recording. Okay. So back to the point of the finite state machine. So we learned from the sequential circuit, there is something called what? Sequential elements. And we started from SR latch. From the SR latch, we learned, all of the flip-flops. That's the historical thing of the flip-flops. And we identify how can we work with the flip-flops by learning the three different tables for describing the relation between input and output. We named them truth table and the characteristic, which is also state table, and excitation table, right? And any table in the world, somebody can ask you to do implementation for it, which is following the same procedure we have learned by K-map, and then Boolean algebra equation, and after that you will go in implementation, whether it can be AND gate, OR gate, non-gate, equivalent to whatever, and so on, as we learned from the combinational circuit and the gate level implementations before, right? And we came into something which is completely scary. It's called FSM, which is called which is called finite state machine. Finite state machine. What we need to know about finite state machine, we need to know some facts, which is basically we have to do what? The flow or the graph representation of finite state machine. And there's something called a state table, which we also learn what state table. Do you agree? From the characteristic table, right? State table and strategy to implement using gate level associated with sequential elements, right? And sorry, and possible optimization. Okay, sounds good. So we came into the FSM as two different approaches we can follow, right? One is called what? Mealy. Another one is called what? Moore. Do you guys remember that?
Yes.
That was from the last lecture, right? So for Mealy, let me turn on this fan. It seemed like it got cold. Anyway, so for Mealy, I follow the follow, right? Every single state is represented as what? Bubble, right? Jumping from one to the other will be represented as arc, right? And it's gonna be informative arc. Why? Because you will define inputs slash outputs. If the input like this, the output will be like that while I'm transiting from one to the other. Okay. Then we came into the point that if I want to implement the finite state machine graph or table, which is both of them identical, right? I have to follow the rules of what? Log to number of states equivalent to number of flip-flops I will be using in the implementation. Make sense?
Yes.
I mentioned that last time, right? Then we came into, we need to learn also application. Mainly, it's dense. That means every single state, and the next and present state, while you are moving with arc, you represent the input and output. That means, it's a good candidate for implementing efficient circuit with low power requirement using less resources on chip. Okay, and you can actually build something that's called asynchronous state machine using the Mealy. You can also do synchronous, but we can talk about what synchronous is synchronous later. Anyway, so far, is it clear what is Mealy?
So Mealy is good for low power consumption?
Low power, it's a low power application. It is nasty, but low power application. Because, you know, in low power application, like you already have a boat, right? And you don't want to use all of the engine fuel. So what you're gonna do, you're gonna throw everything from the boat and you stay by yourself in the boat. So, you know, at least it will take you to the others, it will take you to the shore or whatever, right? Because, you know, you try to use less power. That means the battery will not be drained fast. Okay. Of course, you know, who is our lovely candidates for this? IoT, Internet of Things. Sounds good. What is the example of Internet of Things? My watch. iWatch. Fitbit. Samsung watch, whatever, smartwatch, right? Smart sensors. Like, have you guys seen this light sensor thing? The smart light bulb?
Yes.
So, you know, by your phone, you turn on and turn off, right? Or, you know, you connect it to Alexa and then you say, Alexa, turn on the light. You know what I mean?
Yes.
That's Internet of Things. Of course, you know, later, I swear, if you guys are with me, like for 1 year more, you know, I will teach you all of this tricks. But anyway, there is something here, it's called actually, you know, for the cloud or computing for IoT, you can also learn by yourself. It's called Azure. It's a service from Microsoft. If you are really into IoT. And there is a ton of startup companies built based on the microservice that Azure is providing. Like, you know, forecasting the temperature, put the sensor in the top of your house, make a network of sensor, go sell it to the customers. Customer will be happy and you're happy. A bunch of sensors located in the solar panels, so you would not be charged by Edison. You're actually going to sell electricity to Edison. Many things, you know what I mean? There is infinity of ideas. The industry is, how to say, the market is not saturated. So that means, you know, there is a bunch of stuff is not even exist. You can do it exist. And then, you know, you can earn money or whatever. Okay. Sounds good. How does graph look like? I will just give an example, whatever, right? So the example is going to be like this. You know, I have here S0, S1, S2, S3, bubbles, right? And then, you know, I will just make some weird arc like this. And in each one, input, output, whatever, right? So that if you see something like this, this is what? Mealy. So far, so good? Everybody happy with that?
Yes.
Okay. Now, let's make an example. Let's make example. Just an example like a real one. Actually, you know, in reality, the states doesn't have name. I name it. So S0 and S1 are names I made, right? Normally, the states shouldn't have name. Basically, it's basically 0, 0, 0, 1, and so on. That's why, you know, you're going to end up building with what? With flip-flops, right? So for an instance, you know, if I give you a graph like this, I'm going to take it from one of my examples I wrote in the notes. 0, 0. And I will share with you this document later, okay? 1, 1. And 0, 1. This is going like this. This is going like that. This is like this, you know, like this, and this 1 1 0 1 0 0 1 0 0 0 1 0 and 1 0 and 0 0 and that's it.
So are those one input, one output then?
No, I will show you what you mean. So, you know, if I look to this, first of all, you know, I need to see whether that you guys know what I'm saying. This is Mealy or more?
Mealy.
Mealy.
$5 for everybody, virtual $5.
But what's, we haven't covered more yet, right?
Exactly.
I don't know what more looks like.
No, I talked about more a little bit last time.
I don't remember what more looks like.
Yeah, but you guys forgot it. See, you know, you guys don't listen to me. Anyway, so now this is what Mealy, right? So the second step I'm gonna do in front of you is to convert the graph representation of the finite state machine to be what? To be a state table. To be what? A state table. So a state table can be anything you can imagine in your life. A state table basically is the relation between the present state and the next state while the input and output is changing. So one of the way to write it is basically like what we did with the characteristic table. Do you remember? You know, the present state, and then, you know, I have here inputs, and here is, you know, my next state. Do you remember that? That was our characteristic table or state table on what? On the flip-flops. Make sense? The other way is basically to do like this, you know. Here is, you know, here is the present state. Here is the next state, and here is my output. Of course, the present and the next state will be based on who? You based on the
Qn
input.
and Q plus 1.
Huh?
Qn and Qn plus 1.
No, and also the input.
Oh.
Input is directing us to go where, right?
Mm-hmm.
So for instance here, you know, let's make an example, right? Here, if you notice, I have 0, 0, and I have 0, 1, and I have 1, 0, and I have 1, 1, right? Those are the states I have here, right? I can change the name to make it S0, S1, S2, S3, right? So I name them. So I make it symbolic names, right? I can change the name if I want, right? And this is basically clear in front of me in here, right? I change the names. I make it S0, S1, S2, S3. It's up to you, right? To make it simple for you. But later on, you have to make it what? Numeric, like 0, 0, 1, 0, because there is a story behind it. Okay? So far, so good?
Yes.
Now we have to fill the table. So pretty much we have actually 0, 0. I can actually call it QA, QB. Why? Because from figuring out how many states I have 4 states. Log 2 of 4, that means how many flip-flop I have? 2 flip-flops, right? That's why QA is represented for the flip-flop A. QB is represented for flip-flop B. Make sense? Hello?
Can you explain how you knew that was 2 flip-flops?
Again, now you know how many states I have. 1, 2, 3, 4. Do you agree?
Yeah.
So rule set, you know, how many flip-flops I need to implement this finite state machine is equivalent to log 2 number of states, right? So log 2 of 4 is equal to, so that means how many flip-flop I have?
2.
2. So that means I can call one A and I call the other one B, right? Each one, it has QA and it has QB. Do you agree? Make sense?
Yeah.
Yeah, thank you.
Perfect. Now I'm gonna write here QA, QB. Excuse me. right? The second, for me, it will be this is the present state. I need the next state, right? So the next state is based on what is the input. So basically I can write here when the input equals 0, when the input equal 1, QA plus QB plus QA plus QB plus. What does this plus mean? Next state. Make sense? Then the output also depends on the input, which is basically I0 or I1. Okay, now we're gonna go ahead and say this table, it's a weird table. We can break it to be a long table like this, by the way. So same, all right? So, you know, I can make here 4 possible things. 1, 2, 3, 4. Do you guys agree? So that means, you know, I have here present state 0, 0 or 0, 1 or 1, 0 or 1, 1. So far, so good? Now I'm gonna start looking into my graph, right? In the graph, when I is equal 0, when the input equals 0, right? I'm in the present state 0, 0. What is my next state? Going back to myself. Do you agree? So
Could it also be 0, 1? Oh, but the input is 1.
I'm going back to myself. I'm going back to myself when I see this 0, right?
Right.
So that means, you know, my present is 0, 0, but my next is 0, 0 if my input equals 0. Perfect. Hello. Make sense?
Yes.
Huh?
Now, when his input is 0, in that particular case, the output is what? 0. Super good, right? We'll move to the next. What is the next? Now I'm actually into 0, 0, and I'm heading to what? To 0, 1. When my input is what? 1, and my output in this case 0. So that means, you know, here I'm 0, 1, and still I'm 0. That makes sense? So what I did here, I finished 2 states in one line, right? We'll move to the 0, 1. So if I'm standing in 0, 1, I have 2 possibilities, right? Either that I will go back to myself or I will go to 1, 1, right? I will go back to myself when my input is 1. So I will go back to myself when my input is 1. But when my input is 0, I will go to 1, 1. Inputs, the input, if even 1 or 0, the output is still 0, so gonna be here 0 and 0. Then I continue. I'm in 1, 0 now. Where is 1, 0? I'm in 1, 0 here. 1, 0, it has 2 possibilities. Either it will go back to itself or it will go to 0, 0, right? It can go like this or it can go like that. If it's the input is 0, if the input is 0, I'm gonna go back to myself. So I'm gonna be back to myself. If the input is 1, I'm going back to 0, 0. And luckily, no matter what is the input, the output is 1. So gonna be here 1. Then I cover 3 states and the relation between the present and the next. The only one I have in my hand is 1, 1. So if I go in 1, 1, here is my 1, 1. Either I will go back to myself or I will go back, I will go to 1, 0. So let's do it. So, you know, I went back to myself when is 1. So that means it's gonna be here like this. And I will go to 1, 0 if I'm in the 0.
Wait.
Huh? What? So if it's 0, I'm going back to 1, 0. But if it's 1, I'm going back to myself here. If it's 0, I went back to 1, 0. If it's 1, I'm gonna go to 1, 1.
My bad. I was looking at the wrong arrow.
Right? And let's see what is the current output. No matter what is X, I mean, input is 1 or 0, the output is still 0, so it's gonna be 0, 0. This is the state table, which is coming out of the finite state machine graph representation. Perfect.
Sorry, Professor, can you do that this table the same way you did the first one, like the
Exactly,
cube?
that's what I'm gonna do.
Oh, okay, cool. Thank you.
Don't worry. Anyway,
This one
let's do it.
this one looks different, so it's just throwing me off a little bit.
Let's do it in the other way, right?
Thank you.
What is the other way we learn from the characteristic state table? Boom, boom, right? I have what? I have the present states. And those are the present state, present, right? And I have my input, right? And I have my next state and my output, right? Then you know how many input, how many states this table will cover? 8, because I have 3 here, right? So 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. From that table we don't like, we're gonna fill that table just to see, right? What I said here, I said when it's 0, 0, and the input is 0, I'm gonna back to 0, 0, and in that case, my output is 0. When I'm 0, 0, and my input is 1, I'm gonna be back to 0, 1, and my output is 0. When I'm 0, 1, and my input is 0, I'm gonna go to 1, 1, and I don't have any output. When I'm 0, 1, still I'm here, but my input is 1, so basically I'm gonna be jumping to 0, 1, and my output also 0. When I'm in 1, 0, and my input is 0, I'm gonna be here in 1, 0, and my output is 1. When I'm in 1, 0, oh, scheiße, here, 1, 0, and I'm actually 1, 0, and my input is 1, I'm gonna back to 0, 0, and my output is 1. When I'm 1, 1, here, it's gonna be 1, 0, and 0, or 1, 1, and 0. Voila, we finished. Easy peasy lemon squeezy. Hello. If it's not clear, we can make it clear. Ah. Tell me.
It's clear.
Clear?
Mhm.
You know, everybody, you know, he think it's clear, right in the chat, clear. Excuse me. He's the only one said clear. No, no, no. Nobody even said diamond clear or crystal clear, or like, you know, I don't know, photon clear or something. Oh, somebody said crystal clear. Cloudy. Why? Tell me why it's cloudy. We do it again. Huh?
No, I was just looking outside. It's pretty cloudy outside.
Okay, gotcha. Anyway, so so far it looks okay.
Yes, thank you.
It's a straightforward thing. It's a easy peasy lemon squeezy thing. Anyway, here's my next. Anyway, as I told you that, you know, if I would like to follow some procedure to move from the graph representation to implementation, basically I move to the table, and from the table I do my own work. That makes sense? How I'm gonna do my work? Let's see what is exactly I'm gonna do. So if I want to go to implement this kind of table, I have to pick up an element will be representing a flip-flop. How many flip-flop do we have?
Two.
How many flip-flop elements we learned? 4.
4.
Exactly. I should pick. Excuse me. I think it's better for us to pick up one of them. I think the best way to do it, if I'm not asking you for a specific one, you know, pick something easy for you. Something easy for you, maybe like a D flip-flop or T flip-flop. As you know, I remember it's really easy. You know, T flip-flop, it looked like an XOR, right? D flip-flop, basically, you know, the D will be equal to the next state. Something easy to remember, right? So in that case, I would say, you know, I am going to use T flip-flop for the circuit implementation. Excuse me. What does it mean? It means that I need to calculate the excitation table of the thing in front of me. What does it mean? Again, it means that I have to go ahead like this and write here TA, TB. It's a T flip-flop, right? Then I will apply whatever I know about T flip-flop. You guys agree? Anybody remember what was the excitation table of our lovely T flip-flop? What was the excitation table? I forgot. It's not really hard. I can do it here. Look, if I have Q and T and Q n plus 1, 1, 2, 3, 4, right? If it's 0, 1, 0, 1, 0, 0, 1, 1, right? T equals 0, that means you know J and K are equal 0. That means I'm what? I'm storing. So basically I'm storing, so gonna be 0. 1, that means I'm flipping, so gonna be 1. Then you know here I'm storing, I'm gonna store, and here it's gonna be flip. This is what? This is the characteristic or the state table of the T flip-flop. If I want to get the excitation table, then I will go ahead and do like this: Q n plus 1 and TA 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. Then 0, 0, T is 0, 0, 1, T is 1, 1, 1, T is 0, 1, 1, T is 0, 1, 0, it's gonna be 1. You guys agree? Do you know what I'm doing or not?
So the two tables are the exact same then, right?
I don't know. I mean, whatever it can be. But you know, did you see the revision I made?
Yeah.
See, you know, even I don't remember. The only information I remember that, you know, JK, when it was 0, 0, it was storing. 1, 1, that means we fixed it to be toggling, right? This is information I remember. And also I remember when I say T flip-flop, that means, you know, I take the J and K and make it like one wire. Then if T is equal 0, that means JK equals 0, 0. If T is equal 1, that means JK is equal 1, 1, and I filled everything. See? Didn't take that much time, right? Okay, now, you know, I'm gonna take this lovely table and I will fill TA and TB. So what does it mean? I will go ahead and make a column here. This one and this one will bring me what? TA. So I look at it. 0, 0. What is TA? 0. 0, 0, 0. Then, you know, 0, 1. What is 0, 1? 0, 1 is gonna be 1. Then, you know, 0, 0, 0. Then 1, 1. What is 1, 1? 0. Then, you know, 1, 0. 1, 0 is what? 1. Then, you know, 1, 1, 0. 1, 1, 0. So what I did in front of you, I filled the excitation table of the TA based on the information I got from the state table, which is coming from the finite state machine graph representation. Now I'm gonna do the same thing from QB. So QB 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, gonna be 0, 1, 0, gonna be 1, 1, 1, it's gonna be what? 0, So congratulations, guys. We already did what? TA and TB. How are we gonna make implementation? So who exactly we gonna implement? We're gonna implement the TA, TB, Y based on those three. Perfecto. So how many K-map we're gonna have? How many K-map we're gonna have?
3.
3, exactly. So now you know implementation phase. First K-map, 1, 2, 4. Who is our input? From the left to the right to avoid the orthogonal K-map. It's gonna be QA, QBI. So QA, QB, I 0 1 0 0 0 1 1 1 1 0, right? 0 1 3 2 4 5 7 6. Then another one 1 2 3 QA QB I 0 1 0 0 0 1 1 1 1 0 0 1 3 2 4 5 7 6. The third one QA QB I 0 0 0 1 1 1 1 0 0 1 0 1 3 2 4 5 7 6. Right now we are filling the TA. TA is gonna be the location of M what? M2, right? So gonna be M2 and M5. M2 and
Hey, Professor,
yes,
why do we have 3 K-maps and we only have 2 outputs?
you have two outputs. Seriously, I didn't know. We have
TA
three,
and TB, right?
right? Why is the output?
Oh,
And
okay.
TA and TB.
All right.
Okay, so you know I'm implementing TA. So basically, I'm getting now the equation of the TA as a function of the QA and QB and I equal, right? And then I'm I'm getting the TB, QA, QB and I. And then I'm getting the Y as a function of the QA, QB and I. Right? There it was 1 and 5, right? And the rest are 0 0. Do you guys agree? I think 2 and 5, I believe, right? So 2 and 5, there is no relation between of them, so it's gonna be straightforward. What? Two terms, which is basically group 1 is gonna be QA complement, QB and I complement, or with this one, which is gonna be QA ended with the QB complements, and it's gonna be I. So we build the Boolean algebra representing the relation between the input and TA, right? Now we are looking for TB. Where is our TB? TB, we have 1 and 6, right? 1 and 6, 2 terms also. You know, there is no relation or any grouping, you know, possible grouping we can do, right? So this one is gonna be what? QA complement, QB complement, and I, or with the QA with QB with I complement. Everybody agree? Now we're gonna look to the third in a row, which is Y. So Y here, it has 2, which is basically 4 and 5. So we're gonna go here in 4 and 5. Luckily, we have some grouping here, right? So gonna be one group. So gonna be QA ended with QB complement. Everybody agrees with me?
Yep.
Yes.
Now, time to do implementation, right? So what is the implementation? Implementation is very sorry, it's very straightforward, right? Why straightforward? Because you have to build an flip-flop called T, no, it's not T, I'm sorry. It's called A. And there's another flip-flop, it's called B. And both of them are synchronized. That means both of them using the same clock. If the two flip-flops are not reporting in the same clock, that's called asynchronous implementation. But since both of them using the same clock, that means they are reporting at the same time, that's called synchronized circuit. Synchronized circuit. Why? Common clock source is used to timing input output. Sounds good? This is T flip-flop. So I know that actually it's called here TA, and this is called TB, and this is called QA, and this is QA complement, while this is called QB, and this is called QB complement. You guys agree? Make sense? Now we have extra wire here called I as an input, and we have wire here as output. What we're gonna do, we're gonna look to the equation and make implementation. So TA, that means this input, TA, which is this input, where is it? TA, this input is the QA complement, right? Where's our QA complement? QA complement with QB complement. Going with the I ended like this, right? And then the second term is QA QB, right? So let's have a different color. You guys much better than me in drawing, but QA with QB. Oh, sorry, QA was what? QA with QB, right? With our QB.
Is it QB complement?
No, I'm talking about, oh, you're right. You know what? Just clear up this. But you understand what I'm saying, right? It's just a matter of how to implement it in a nice way, I'll try to do it in a clean way, Either that you just use QA and flip it, that's fine. But anyway, now we need to do the game from scratch, right? So I have I is associated in the TA, right? So I have TA is QA complement with QB, right? So QA, right, with QB complement. Do you agree? And they're gonna be together ended in a cluster. They're gonna be with QA. Why I do this? This here, right? QB complement, and they're gonna be with I complement. So we have to do what? So this is the first step, right? Then they're gonna be QA with QB. Did I make a mistake?
No, it's a QA complement.
Basically, I implemented this, right?
Yeah, you implemented the back one. Now you're
I
doing the
implemented this
second one.
one, but I need to make this I, right? So I have to go back here and make it I. You're right. I implemented the second term, basically.
That's right.
This is the second implemented, right? Then now we are in this one, right? So this one is QA complement, right? QA complement. Going where? With QB, right? And what is associated with it? Normal, gonna be I complemented, right? Those three will be ended, and then I'm gonna what? OR them together. What the heck? And then I will OR them together, and that will be my TA. It makes sense? Okay. Hello.
Oh yeah. Uh-huh.
Mhm.
And you're gonna do the same thing with the what? With the TB. So let's
Actually, wouldn't that be your TB?
Hmm?
Wouldn't that be your TB?
What is W?
No, you did it for TB, didn't you?
No.
That was
Oh yeah, I
TA.
think you did.
No,
yeah,
that
you,
was
no,
T-
you did. No, TB. QA, QB, I, and then
QA,
I.
QB complement, right?
Yeah.
So, we're gonna extend wire here. You're gonna be here in OR gate, and then you have here two AND gates. You understand what I'm saying, 1, 2, 3, 1, 2, 3, and you're gonna do the same thing like this. I'm not gonna do it because gonna be big mess. You're gonna organize it, okay?
Yeah, but for that circuit, that was for QB, not. I mean, that was for TB, not TA.
No, he did it for TA.
He
No, I
did.
did here.
Yeah.
Okay, never mind.
He underlined TB, but he can remove that. There you go.
Much better, right? Okay.
So
Now we're gonna make Y, right?
Okay,
Y is
yeah,
easy.
Y.
Y is clean, right? Here, and then QB complement, right? And them together, this is Y. So what you have in front of you is what is the implementation of the finite state machine graph representation. We started from the beginning. Sound easy, busy, lemon squeezy?
Do we have to draw the clocks together if they're synchronous, or can we just say that they are?
I mean, I said here clock. I mean, you can connect it,
Yeah. It doesn't matter.
I don't want to make a mess, so you guys will be like confused,
Okay.
right? So
Can we just assume that it's usually a synchronous circuit?
Yeah, that's why I said it's synchronized here, right?
Okay.
Make sense?
Yeah.
What is possible question I can bring in exam?
Sorry, one last question. Is the is the inputs, is it only one inputs per the flip-flop? Oh, because the T flip-flop. Got it. Never mind.
Come on, you have to pay
Yeah.
$5.
Never mind. I answered my question.
No, you're fine. Okay.
Go back to the key map.
So he gonna pay $5 for the key map? Why?
No, can you go back to the key map?
Yeah, sure. You. Is there something in the key map?
I just wanted to see it just one more time,
What exactly I want? Tell me.
just so I could like get a visual and then put it together.
Hmm?
It was just together, like just to like put it together all together in my mind.
How I filled the key map?
No, I mean like the whole problem, like the whole.
Here. I
No,
filled.
no, it's fine. It's fine. It's all good.
Okay. Tell me. What's the question? Tell me. Hello.
I think you just wanted to look at the K map.
Sure.
Yeah, I just want to look at it and then we're all good. Thumbs up.
Okay.
Question.
Anyway, let's see that Professor Ali would like to be evil. So how I'm gonna be evil? Let's think about scenarios. What is the scenarios?
We create our
Multiple
own
states?
schematics.
Exactly. No, actually, I will give you the schematic and ask you for the finite state machine. Yes, I'm evil. You understand what I'm saying?
Yeah, trying to make the truth table is just
Basically, I will give you this circuit and ask you for the finite state machine graph representation.
it's like, what is that?
You have to work.
So you gotta work backwards. Yeah, my brain doesn't
It's
work
gonna be
backwards.
backward. Yes, exactly. Do you want to see it how it's actually backwards?
You
Is
just
it easy?
you just look at it, right?
Wait. Is it easier? Is it easier to go from this to the state machine,
It
or
is
is it?
very easy. It is the straightforward thing ever I've seen in my life. You know why? First of all, you're gonna start up. You need to get the equation of the TA. You need to get the equation of the TB. You need to get the equation of the Y. Then you will start filling the state table based on this information. And based on how many flip-flops you have, how many states you're gonna have. You got it?
Yeah.
So if I look at this one, right? Let's look at it together, right? This is my question for you in the exam, and I'm asking you for finite state machine diagram. What are you gonna do? I mean, graph representation is diagram. Okay. So basically, I need to answer myself: what is TA, what is TB, and what is Y as an output, and then I will write them here in equation, right? Also, I learned that I have 2 flip-flops. So how many states I have?
4.
I have 4 states. Perfect. So then I need also 4 states, right? Let's start getting this. What is TA here? TA is 2 sources. That means there is 2 elements into it, and here's just 2 elements into it, and here is just 1 element. This one is straightforward, right? It's QB.
Wait. Sorry. How did you get 2? How did you from there? You saw 2 sources.
Did you see this
Gates.
or?
Yeah, it's the 2 gates.
Two branches.
Okay.
2 branches.
2 branches again.
$25. So two branches. So auto, that means I'm adding, right? So basically
Okay,
here, add here, right? Group first one is like this one, right? It's basically QA with QB complement, right? QA, QB complement with normal I, right? And the second group is I complement with what? QA complement QB. Right? Why? Why is very easy, right? Why it's QA and QB complement. QA with QB complement.
Oh, it's the wrong one. Yeah.
QA, QB complement. Seems that I didn't eat what. Anyway, so I didn't have my breakfast. So
$5. $5.
Come on, you guys have to give me money and I will give you the Okay. Anyway, let's go on the TB, right? TB is what? I didn't draw it, but we will just steal it from here, right? Let's steal it from here. So it's gonna be QA complement QB complement I, and then QA QB I complement, the reverse QA QB I complement, right? I have the equations. I know 4 states, so I will start build my table, right? I know it's a 4 states, so that means I need 2 what? QA and QB. QA, QB, and I have I as an input, and I know that it's a state table, so that means there is QA plus, QB plus, and I know I have Y. Right? Do you guys agree? But somebody will come and say, but you got me TA, right? He didn't give me what? He didn't give me QA plus. Do you guys agree?
Yes.
Easy peasy, lemon squeezy. If I look to the tools table, I will find the relation between T and Q reverse.
Sorry, what? Say that one more time.
This table showing me T and QN, what is the relation between of them? The characteristic table of T, right? You understand what I'm saying?
Are we looking at the bottom table or the top table?
This one, this one, this one. I said something wrong, and I'm waiting for you guys to say it's wrong. Something was wrong.
Well, it's not flipped, right?
Exactly. So basically, the only way to do it is to go here and create something called TA. TB.
Uh-huh.
So you need actually to clear this a little bit. And you will say that I have TA, TB, and then from there, I will have QA plus QB plus, and I have Y. So I will start filling the 8 state 1, 2, 3, 4, 5, 6, 7, 8. I know those, right? I'm right. What I can do, I can take every single state and I compensate it in the equations. Then I will produce TA and TB and Y, straightforward, right? Then
Yes.
TA and TB, I have them, and I have the Q for each A. So then, you know, from the TA and QA, I can get the QB using the state what? State table of the flip-flop, this one. Boom. Then I get the next state. Then I will go ahead and draw it. Then everybody will be happy.
Oh yes, Jason, that makes sense more because
That makes sense?
we have that characters table.
Yes. I mean, I'm not gonna give it to you, but you know, did you see how I created in front of you? Nothing, right?
I just remember it's the XOR table.
You know, I will give you another example, right? If it's D flip-flop, it's easy. D flip-flop much better. You know why? Because D flip-flop, D is equal Q plus 1, right? So then I can actually remove the DA and I will put it actually equal the Q plus. Can I work out the table? But you know how much you're gonna pay? You didn't tell me. Anyway, let's go ahead and do it, you know. Okay, that's fine. Now, you know, I have QA, QB, he gonna pay me $10. That's free. Anyway, so it's gonna be 0, 0. Let's go ahead and do it. You know, TA is basically on 0. Anything times 0 is 0. Do you guys agree? My QA is 0. My
Yes.
QB is 0. The output of TA is equal what? 0. Right?
Yeah.
Then I will follow. You know, I have 0, 0, 1. It's still 0, right? Then, you know, I have here 0 and 1 and 0. Let's see it. 0 and 1 and 0. 0, 1 and 0. Here, they're going to be 0. They're going to be 1, right? Here we're going to be 1. Here we're going to be, Q is what? Q is what? You know what I'm doing, right?
There's going to be a 0 in both sides of the equation for everything.
So let's do it. Let's
Yeah,
do it. Let's do
0.
it. You know, let's do it one by one. QA is 0, right? So I have here 0 and QB is 1. So gonna be here 0 and I is equal 0, right? So this is actually 0, right? And I is 0 to gonna be 1. QA is still QA is 0 to gonna be here 1, and QB is what? Is 1, right? So this actually 1 ordered with 0, so the output is 1. Make sense?
Mhm.
And you will continue. So let's do it. So now I have 0, 1, 1, right? So 0, 1, 1. So gonna be here what? Gonna be here 0, 0, and 1, right? There, 1 is gonna be what? 0. So they're gonna make it 0. So gonna be 0. Then you know 1, 0, 0, right? 1, 0, 0, right? This guy was what? Gonna be 1 and 0. This is out. Then you know 1, 0, 0. So 1, they're gonna be 0 also, right? And then you know 1, 0, 1, 1, 0, 1, 1, and that 0 is gonna be 1, and this 1 is gonna be 1 is enough. It's gonna be 1. Then you know 1, 1, 0, right? 1, 1, 0 gonna be 1, 0, 1, 1, 0, and 0 gonna be here 0, and there we're gonna be what? 1, and you know the Q gonna be 0, so it's gonna be 0, right? Then you know 1, 1, 1, it's gonna make it what? 1, 1, 1.
0. Because you'll have a 0.
So I fill the TI. You guys will fill the TB. Make sense? I mean, it's just like compensation, right?
And you said to use the state table to find QA plus and QB plus.
So now, now I'm gonna do what? I'm gonna take this, and that will define to me QA plus, right? Based on what? Based on that.
XOR table.
Yeah, where is it? Where did it go? Here, right? So we are looking for anyone is like an XOR, okay? So gonna be like an XOR. So we go here, right? 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0 is 1, 1, 1 is 0, 1, 0 is 1, 1, 0 is 1. Y is easy, right? Y is very easy. QA, QB, right? So Y is basically based on what? QA it has to be 1 and QB it has to be 0, right? This is the only way that Y is gonna be 1. Do you agree? So we're gonna look to anything 1, 0, right? 1, 0, 1, 0. So gonna be here 1, 1, and the rest will be here zeros. Now if you want to get this one, you have to get this one, and you will be done. After that, it's gonna be very straightforward. The table will be filled, right? So you can start drawing it. Like they're gonna be what? They're gonna be what? They're gonna be the next, the next, the next, the next, the next, the next. And here is the present, 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 the present. Here is the input, and here's the output. Make sense? Any question?
Sorry, is it QA plus that's the next?
What happened?
Not the TA, right? Not TA is not the next, right? It's QA.
No, TA is out. TA is like internal. TA is like internal state helping me to get the next state.
Oh.
So I cannot get this fast, right? So what I did, I got this, and from this I got this. Then these two guys will be doing the work with us.
Mm-hmm.
But our bubbles would be QA and QA plus, right? Not TA.
Exactly.
Okay.
Exactly. As we did in what? Here. Look, this.
Yeah, that's the QA. Yeah, okay. That's the QA.
You don't need those. Make sense? Any question? Any answer?
So what does this have to do with the 4 states that you wrote above?
Huh?
Can you scroll up just a little bit?
Sure.
Right there. When you wrote 4 states, what does that come in?
That came from where? From here, right? There is 0, 0. That's a state. There is 0, 1. That's a state. There is 1, 0. That's a state. There is 1, 1. That's a state. 4 states, right?
Okay.
And
All
same
right.
thing here, right? So you basically end of the day, you're gonna be drawing 0, 0. 0, 1. 1, 0. 1, 1, right? And then you will start looking. Oh, 0, 0 going to whatever. 0, 0 is going to something else. 1, 1, and 0, and here is the output. You know what I mean? You understand what I'm saying?
Yeah, sounds good. Thank you.
You're welcome. Okay. Any question? Any questions?
Nope.
Straightforward.
Is this going to be on our exam on Wednesday?
It should be. So the exam is gonna be the following. Gonna be sequential, associated with some combinational circuit. Because this is accumulated course, right? I have to use K-map all the time as an optimized way, optimization. I know I need to use truth table. It's truth table. It's a design rules, right? I have to use the Boolean algebra. It's a design rules. You know what I mean? But at least, it's very clear to you what I'm saying, right? There is a graph representation. You're moving to the truth table, the state table, and from the state table, you go to the implementation. Now, if I'm in implementation, I can get from the implementation back to the state table. And from the state table, I will go back to the finite state machine diagram or finite state machine graph representation, right? How did I do all of this? Because I learned that there is something is called sequential elements. It started by latch, and then from the latch, we improve it to be SR flip-flops. We figure out there is a problem in SR flip-flop. We move into the JK flip-flop. We fix it, the JK flip-flop. We move to the D flip-flop and T flip-flop as a special cases coming from the JK flip-flop. it's, you know, it's like a chain, right?
Professor, so for the Wednesday, we're not meeting, right?
We're not.
Are we meeting in class? On
No, 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 no. It's gonna be the same story. I'm gonna give you the whole day.
Okay, the whole day. Okay.
Yeah, I will give you the whole day from 8 o'clock in the morning till midnight to submit your answers. Then I will be working in a weekend or so. When I have time, I will grade it, and then I will post it on your Blackboard. You will find automatically is posted on the Blackboard, and also there is a room for the grid scope to see, you know, all of my like itty bitty derivation of which is what and which one is costing you what in terms of the if there is a partial credit or whatever. Okay.
Okay, sounds good.
Any questions? I honestly, sequential circuit is straightforward. You just need to practice. There is no way for you to go exam without practicing. Do you guys agree?
Yeah.
Yep.
But fundamentally, it's really straightforward, right?
Yes.
Promise me to practice, please. Do your best, practice. If you have any questions, I'm here to help and assist. Copy of this note, so you know, the one I just wrote by my hand in front of you, it will be posted on the, are we in week what, 11, right? Week 11, the recorded of this lectures will be also there as a link for YouTube. And then, you know, there is some documentations I already created a couple of years ago or something by my hand. I will post it there if it's actually really helping you. Okay. The only thing is actually required from you is to practice, 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 practice. Sounds good?
Yep.
Okay, so I want to thank all of you for the time and efforts and for attending the course due to this, you know, during this headache of the pandemic and so on. I hope that all of you are secured and safe, and God bless all of you. Happy nice Monday. Enjoy the rest of your Monday, and you know, and then, you know, hopefully all of you will get A and a final grade on the Wednesday midterm exam. I think so. I think you guys can do it. It's doable. Okay.
Thank you,
Have
Professor.
a nice one.
God bless you guys. Thank you. Bye-bye.
Thank you, Professor.
Thank you. Bye-bye.
Okay, question, Professor. Quick question.
Good question.